When we talk about video games, we usually talk about worlds. We talk about the towering, neon-soaked skyscrapers of Night City, the desolate, wind-swept ruins of Lordran, the hyper-realistic, mud-caked trenches of Battlefield. But beneath the surface of every digital world, there is no mud. There is only a pulse, a heartbeat of pure mathematics, a framework of code that dictates how gravity pulls, how light bounces off a wet cobblestone, and what happens when a player presses the jump button. This invisible framework is the game engine. Before game engines existed, every video game was essentially an island. If you wanted to make a game in the 1980s, you had to write everything from scratch. You had to teach the computer how to draw a pixel, how to play a sound, and how to read a controller input every single time. Today, a single high school student in their bedroom can download a piece of software and conjure a photorealistic forest that rivals blockbuster movies, complete with simulated wind and real-time bouncing light. How did we get here? How did we move from writing raw assembly language on punch cards to wielding virtual tool sets that build entire universes in real time? This is the story of the tools that built our childhoods. The story of proprietary secrets, open source rebellions, and the relentless, exhausting pursuit of absolute reality. In the early 1990s, the video game industry was flat. Two-dimensional platformers and top-down shooters ruled the world. But deep in the offices of ID Software, a brilliant programmer named John Carmack was about to crack the Z-axis. In 1993, ID Software released Doom. Doom didn't just revolutionize the first-person shooter, it revolutionized how games were made. Carmack created what we now call id Tech 1, often simply referred to as the Doom engine. It wasn't truly 3D. It used a clever mathematical trick called raycasting to render 2D maps in a way that tricked the human eye into perceiving depth. But its real innovation was its modularity. Carmack separated the game's core code from its art assets. This meant that players could easily swap out the graphics and sounds without having to rewrite the game. This birthed the modding community, and the concept of an engine as a reusable foundation was solidified. A couple of years later, in 1995, a young prodigy named Ken Silverman developed the Build Engine. Licensed to 3D realms for Duke Nukem 3D, the Build Engine pushed pseudo 3D to its absolute limits. It allowed for sloping floors looking up and down, and highly interactive environments. You could break glass, flip light switches, and blow holes in walls. The strength of these early engines was their blistering speed on limited hardware. Their weakness? They were ultimately built on optical illusions. To achieve true, uncompromised 3D, the industry had to leave the tricks behind. It was time to start calculating real geometry. By the mid-2000s, 3D gaming had matured, but characters still moved like animatronics and worlds felt bolted to the floor. In 2004, Valve changed the paradigm with the release of the Source engine, debuting alongside Half-Life 2. Source wasn't just about looking better, it was about feeling real. Valve deeply integrated the Havoc physics engine into Source. Suddenly, wood splintered dynamically, and physics puzzles became core gameplay mechanics. Source also introduced groundbreaking facial animation tech, giving characters a level of emotional depth previously unseen in gaming. The Source engine was a masterpiece of kinetic feel. Portal, Left 4 Dead, Counter-Strike, Global Offensive, they all share that distinctly crisp Source movement. But as the years went on, its aging architecture became notoriously difficult for developers to untangle, often described affectionately as spaghetti code. While Valve was perfecting physics, a German studio named Crytek was chasing absolute visual supremacy. In 2004, they released Far Cry, built on the CryEngine. 3 years later, they released Crysis. CryEngine was a beast. It introduced real-time dynamic lighting, incredibly dense foliage, and vast open-world draw distances that brought the most powerful PCs on Earth to their knees. It birthed the most famous hardware meme in gaming history. But can it run Crysis? Its strength was its raw, unadulterated power. If you wanted the best-looking game on the market, you used CryEngine. But its weakness was its hostility to developers. It had a steep, punishing learning curve, and optimizing it for consoles was a nightmare. As the Xbox 360 and PS3 generation boomed, mega publishers realized they were spending millions on engine licensing fees. The corporate mandate became clear: build it in-house. Enter the Frostbite engine developed by DICE in 2008 for the Battlefield series. Frostbite was a marvel of audio-visual engineering, renowned for levolution, real-time, large-scale destruction. If there was a wall, you could blow a hole in it. But Frostbite exposed a major danger of proprietary engines. It was built explicitly for first-person shooters. When Electronic Arts mandated that all their studios, including BioWare, use Frostbite for role-playing games, development became a living hell. The engine simply didn't understand things like inventory systems or branching dialogue, forcing developers to build these basic features from scratch. We saw similar stories across the industry. Ubisoft built the Anvil engine for Assassin's Creed and Snowdrop for The Division. CD Projekt Red built the stunning Reed engine for The Witcher 3 and Cyberpunk 2077. While these custom engines created bespoke masterpieces, they required armies of engineers just to maintain them. The tech debt was staggering. Eventually, even CD Projekt Red threw in the towel, announcing they were abandoning the Red engine to use a third-party engine for their future Witcher games. The era of every studio building their own engine was ending. The industry was consolidating. While AAA studios were building billion-dollar proprietary beasts, a quiet revolution was happening in the indie scene. Launched in 2005 from a basement in Denmark, Unity wasn't designed to make the most photorealistic games in the world. It was designed to make game development accessible. Before Unity trying to release a game on PC, Mac, PlayStation, and mobile meant rewriting massive chunks of your game for each platform. Unity promised a holy grail: build once, deploy anywhere. It featured an incredibly user-friendly component-based architecture. It used C#, an accessible programming language. And crucially, it launched the Asset Store, allowing solo devs to buy pre-made 3D models, animations, and code snippets instead of making them from scratch. Unity democratized game development. It practically birthed the modern indie scene and entirely conquered the mobile gaming market. Today, roughly 70% of top mobile games run on Unity, but it wasn't perfect. For years, Unity suffered from a reputation of bloated performance in heavy 3D titles. And then there was the trust issue. In late 2023, Unity leadership announced a runtime fee, attempting to charge developers every time a user installed their game. The backlash was apocalyptic. Developers threatened to delete their games en masse. Though Unity walked back the changes, and by the release of Unity 6 in 2026, returned to a standard subscription model, the cultural damage was done. The indie community realized the danger of building their livelihoods on closed-source, corporate-controlled software. They needed a sanctuary, and they found one. Enter Godot. Originally created by Juan Linietsky and Ariel Manzour, Godot was open-sourced in 2014 under the MIT license. This meant it was completely free. No subscriptions, no royalties, no corporate overlords who could suddenly change the pricing terms. You own your game forever. For a long time, Godot was seen as a cute hobbyist tool. But over the last few years, especially with the release of Godot 4, it has become a powerhouse. Godot's architecture is uniquely elegant, based entirely on a node system where everything is treated as a nested scene. It's incredibly lightweight. The entire engine downloads as a single file under 200 megabytes and launches instantly. While Unity forces 2D games to exist on a flat plane in a 3D world, Godot has a dedicated native 2D rendering engine, making it the absolute gold standard for 2D platformers, RPGs, and pixel art games today. Godot's weakness? It is still catching up in the AAA 3D space. If you want hyper-realistic graphics, global illumination, and massive open worlds, Godot will require a lot of heavy lifting. But for indie developers, Godot represents something more than just an engine. It represents creative freedom. If Unity democratized game development and Godot liberated it, Unreal Engine conquered it. Created by Tim Sweeney and Epic Games in 1998, Unreal started as the backbone for a single arena shooter. Through the 2000s and 2010s, Unreal Engine 3 and 4 became the default choice for AAA studios. Epic continuously reinvested the billions they made from Fortnite straight back into the engine, buying up cutting-edge tech companies and integrating them for free. Unreal Engine 4 introduced Blueprints, a visual scripting system that allowed artists and designers to create complex gameplay logic by connecting nodes on a screen, without writing a single line of traditional code. But then came Unreal Engine 5. Epic achieved what was long considered the holy grail of real-time rendering. They introduced two god-tier technologies. First, Lumen, a fully dynamic global illumination system. Instead of developers pre-baking lighting, Lumen calculates light bounce in real time. If you blow a hole in a roof, sunlight instantly floods the room exactly as it would in real life. Second, Nanite, virtualized micro-polygon geometry. For decades, artists had to optimize 3D models by reducing their polygon count so the game wouldn't crash. With Nanite, that limit evaporated. You can drop a cinema-quality billion polygon statue straight into your game, and the engine seamlessly scales it on the fly. By 2026, with the release of Unreal Engine 5.8, Epic has pushed the boundary even further, introducing production-ready tools like megalights for infinite shadow casting lights and paving the road for Unreal Engine 6, where entire live ecosystems and generative AI toolsets are built directly into the editor. Unreal is no longer just a game engine. It is used by Hollywood to render backgrounds for The Mandalorian. It is used by architects to design skyscrapers. It is the apex predator of real-time 3D. Its only real weakness? The sheer weight of it. It requires massive file sizes, beefy hardware, and a team of specialists to unlock its true potential. If you are sitting at your computer right now, ready to make your dream game, which engine do you choose? There is no best engine anymore. There is only the best engine for your project. If you are a solo indie developer working on a $0 budget and you want to make a 2D game, a stylized 3D platformer, or a retro boomer shooter, Godot is your champion. It is lightning fast, highly intuitive, and carries absolutely zero financial or licensing risk. If you are building a commercial game aiming for iOS, Android, and Nintendo Switch simultaneously, or if you are making a complex 3D strategy game, Unity 6 remains incredibly powerful. It still has the best mobile monetization pipelines, the largest library of pre-made assets, and an ocean of tutorials online. But if you want to make the next great AAA cinematic experience, if you want hyper-realistic humans, vast open-world lighting, and cutting-edge visual effects, if you want a job at a major AAA studio, you learn Unreal Engine. It does out-of-the-box what would take years to program in other software. The evolution of game engines is the story of removing barriers. In the beginning, creating a video game was an exercise in extreme mathematical restriction. It was an exclusive club for elite computer scientists hacking hardware limitations. Today, the barriers are gone. The tools used to create the most profitable entertainment products on Earth are entirely free to download. The engine handles the gravity, the lighting, the collision, and the physics. All that is left for you to provide is the imagination.